Welcome to Savi YouTube channel from Sai Vidya Institute of Technology, Bangalore. So, in the last session, we have started the new theorem, that is maximum power transfer theorem, and we derived the condition of maximum power transfer by considering different types of sources and different types of loads. So, we have considered three cases. First case, when we consider DC source with the source resistance, and if the load is purely resistive and if it is variable, then the condition for maximum power transfer is the value of load resistance must be equal to the value of source resistance. Case 2, we considered AC source, just change the DC to AC source and keeping the load same. When you consider the AC source, we have considered the source impedance as ZS, that is equal to RS plus JXS. This is the source impedance, and keeping the load same, we derived the condition for maximum power transfer. Then in that case, the value of load resistance must be equal to the magnitude of source impedance for maximum power transfer. Case 3, I am keeping the source same, that is AC source only, and we have changed the load to complex load, where we have RL and XL, both are variable. In that case, the condition for maximum power transfer is the source, that is the load impedance ZL. If I consider ZL as load impedance, that should be equal to the complex conjugate of source impedance. So, this is what discussed in the last session. So, in this session, let us work out some problems on maximum power transfer theorem. Now, what we should do in maximum power transfer theorem to solve the problems? First, for the given problem, we should obtain Thevenin's equivalent circuit. That means, just if you know the Thevenin's theorem, so you know how to get the Thevenin's equivalent circuit for the given network. Once we get the Thevenin's equivalent circuit, then apply the condition of maximum power transfer for that circuit, depending upon which circuit it is, whether it is a AC circuit or DC circuit, or what should be the load, the value. Depending upon the problem, that is data, we can decide what should be the condition for maximum power transfer. Now, let us work out the problem for each case. Let us solve one problem for each case. Now, let us see the problem statement. So, find the value of load resistance. You have to find the value of load resistance when maximum power is transferred to it. If you want to transfer maximum power to this load resistance, what should be this value? So, after finding the value of load resistance, you have to find the maximum power transfer to it. That is the problem statement. To solve any problem on maximum power transfer theorem, first you have to convert the given network into Thevenin's equivalent circuit across the load terminals A and B. That means, this part of the network, you have to convert it into Thevenin's equivalent circuit. That is, a voltage source V Thevenin in series with a resistance R Thevenin. This is Thevenin's equivalent circuit. So, let us find first Thevenin's equivalent circuit. Okay. First step 1, to find V Thevenin. So, what is V Thevenin? You know already. V Thevenin is nothing but open circuit voltage across the load terminals. So, load is given here. So, to find the open circuit voltage, what I should do? I should create the open circuit. To create the open circuit, I should remove this load. Let us remove the load, create the open circuit and find this voltage between A and B, that is your V Thevenin. How to find the voltage or current in any network? Either you have to go for KVL or KCL. Now, let us solve by mesh analysis. Let us take this loop as I1. Let us take this loop current as I2. So let us apply KVL now. Applying KVL to loop 1. Applying KVL to loop 1. So 8 I1, only I1 is flowing here, plus 4 I1 minus I2 is equal to minus 2 plus V, plus 5 volts. So sum of all the voltage drops in the given network or a loop is equal to algebraic sum of voltage sources. That is 8 I1 plus 4 I1 minus I2 is equal to what? 5 volts. If you simplify, you will get 12 I1 minus 4 I2 is equal to plus 5. Now KVL cannot be applied to second loop because you have a current source. But I can write one current equation, I cannot write voltage equation. So this current source, current value is 2 ampere flowing upward. In the same wire, loop current is flowing downward. Hence, I can write here I2 is minus 2 because it is opposite. So, but what is I2? Is equal to minus 2 ampere. So, substituting here, we will get 12 I1 minus 4 into minus 2 is equal to 5. We will get 12 I1 is equal to, so minus into minus plus 8, take right hand side, it becomes 5 minus 8. Therefore, 12 I1 is equal to minus 3. Okay. Now, what is I1? I1 is equal to minus 3 by 12. It is equal to minus 0.25 ampere. So, you got I1 value, you got I1 and I2 both. Now, my intention is to find V Thevenin. So, what is V Thevenin? Voltage between these 2 points is V Thevenin. Therefore, I can write, if I take the potential of this point as VA, if I take potential of this point as VB, so V Thevenin is equal to what? V Thevenin is equal to VA minus VB. Correct? Potential of these 2 points, potential difference between these 2 points is V Thevenin. You can solve V Thevenin by any method, just I am going by this method. So, to measure the voltage at this point or voltages at any point in a given network, we need to take one reference point. So, let us take a reference point always in the bottom line. Then if I take this as reference point, then VB becomes 0. If VB is equal to 0, then what is V Thevenin? V Thevenin is equal to VA. So, always when you are finding V Thevenin, one of the point we take it as reference point. So, I am taking this as reference point. So, VB equal to 0, therefore, V Thevenin is equal to VA. So, if I find the potential of this point, that is equal to V Thevenin. Let us find the potential of this point with respect to ground. So, when you want to measure the voltage at any point, you have to move from the reference to that point where you are interested to find the voltage. To reach this point, you have many routes. You can go by this way, you can go by this way, you can also go by this way. This way you cannot go to measure the voltage because on the way you have a current source. When you are having a current source, you cannot measure the voltage. That is why you have 2 paths. Either you can go by this way or you can go by this way to measure the voltage at this point. Whichever the way you go, you will get same answer. Suppose if I prefer to go by this way, you have to write the polarity of voltage drops in that path. In this path, polarity is already written. So, here I should write the polarity of voltage drop. Polarity of voltage drop depends upon direction of current. We are assuming current flow I1 like this, and this is positive, this is negative. So, write the polarity of voltage drop. Then come here, you cannot write the polarity of voltage drop because no current is flowing here, because open circuit in 2 ohm no current is flowing here. Here you have a voltage source and polarity is there. Therefore, measuring the voltage voltage VA from reference VA is equal to what? Let us move like this, minus to plus, plus 5, plus 2 minus, minus 8 into I1, again plus 2 minus, minus 2 volts. That is the equation for VA. So write the equation, minus to plus, plus 5, plus 5, plus 2 minus, minus 8 I1, plus 2 minus, minus 2 volts. Here open circuit current is 0, voltage is not 0. You should not forget to write this voltage source value. Open circuit current is 0. So hence voltage drop across this is 0. Open circuit voltage is not 0. Always open circuit voltage will be there. That's what you are measuring here. Now substitute the value of I1 here, then find the value of VA. What is the value of I1? Minus 0.25 ampere. Substitute and find it. Substituting the value of I1 minus 0.25 will get 5, minus into minus plus, 8 into 0.25 is 2, this is minus 2. Therefore this get cancelled, we will get VA is equal to 5 volts, that is nothing but V Thevenin is equal to VA is equal to 5 volts. That is, you got the open circuit voltage is equal to 5 volts. Okay, you got first parameter. Then what is the second parameter you should find? Step 2. Step 2, to find R Thevenin. To find R Thevenin. How to find R Thevenin? Since in this network you don't have any dependent sources, it is very easy to find R Thevenin. What is the procedure? You have to make all the independent sources 0. Anyhow, don't have dependent source, but you have only independent sources. You have to make all the independent sources 0. How to make independent sources 0? If there is a voltage source, you have to create the short circuit. If there is a current source, you have to create open circuit. Then looking into the same open circuited terminals, you have to find the total resistance of the circuit. That is your R Thevenin. Okay, now let us find. Okay, now your intention is to find R Thevenin looking into the open circuited terminals. Let us find now R Thevenin for the network. So you have to make all the independent sources in the network 0. You have a voltage source. The voltage source is made 0 by creating short circuit. Now let us create short circuit. Okay, you have a voltage source, create the short circuit. Okay, short circuit. You have a current source, create open circuit. Open circuit means just remove it, remove this. Okay, now this is your new network to find the resistance. Then if you observe this network, this resistance and this resistance becomes parallel, because if you take the resistance 8 ohm like this, 8 and 4 ohm becomes parallel. That comes in series with 2 ohms. Therefore R Thevenin is equal to 8 parallel with 4 comes in series with 2. That is your R Thevenin. So what is 8 parallel with 4? 8 into 4 divided by 8 plus 4 plus 2, that is equal to 2.66 plus 2, this 2.66, that gives 4.66 ohms. That is your R Thevenin. Now you got V Thevenin, you got R Thevenin. Then what you should do? Step 3, you have to get Thevenin's equivalent circuit. Step 3, Thevenin's equivalent circuit and connect the load across it. What is Thevenin's equivalent circuit? V Thevenin in series with R Thevenin. So R Thevenin is what? 4.66 ohms. What is V Thevenin? 5 volts across AB. That is, you have converted the given network into Thevenin's equivalent circuit. What is your intention? You have to find the value of load resistance for maximum power transfer. So you have the load resistance here, you have the load resistance, then what should be the value of load resistance for maximum power transfer? Now, what type of network was given? It is a DC network, because no inductor, no capacitor was shown, and hence it is a DC source, and source resistance is R Thevenin. Then what type of load it is? Resistive load. So when the source is a DC, load is purely resistive. So what is the condition for maximum power transfer? The value of load resistance must be equal to the value of source resistance. So that is when here condition for Pmax, maximum power transfer, is RL should be equal to RS. That means the value of load resistance must be equal to source resistance. What is source resistance here? That is R Thevenin itself. Therefore, RL should be equal to 4.66 ohms. RL should be equal to 4.66 ohms. That means you are not doing anything here in maximum power transfer theorem, just you are applying Thevenin's theorem and converting the given network into Thevenin's equivalent circuit. Finally, to find the value of load resistance, we are going to apply the condition of maximum power transfer, whatever we derived in the earlier sessions. Now, you got the value here. What is the value? 4.66. So, after finding this, you have to also find maximum power transferred. So, what is the power transfer to it? You have to find. To find that, take just current here, load current IL, and find the current IL. Then power is equal to I squared into RL. That's all. Okay. So now the current is given by IL equal to V Thevenin divided by R Thevenin plus RL. Substitute here, we will get 0.536 ampere. Now what is the power equation? The power equation Pmax is equal to I squared into RL. So I is what? 0.536 whole square into what is RL? RL is 4.66. That gives power. What is the value of power? Power is given by 1.33 watt. 1.33 watt. This is how to solve the problem using maximum power transfer theorem. Now let us solve one more problem for case 2. Okay, let us solve another problem on maximum power transfer theorem. The problem statement is same as earlier problem. Find the value of load resistance for maximum power transfer condition. Then after finding the value of load resistance, you have to find what is the power transfer to it. Okay. First, what you should do, or to convert the given network into Thevenin's equivalent circuit. Which is your load? Load is given here. You have to find the value of load resistance here for maximum power condition. So let us mark the load terminals as A and B for your reference. So first let us obtain Thevenin's equivalent circuit across the terminals A and B. Here we have a practical current source. If you want, you can convert this into voltage source also, or you can keep it as it is. Suppose if you convert this into voltage source, you know that V is equal to I into R. What is I value? 2 at an angle minus 90 into what is R? 4. That gives what? 4 into 2, 8. Angle is same. That is what? Voltage source value. In series with the same resistor, 4 ohm you should write. So here I have converted current source into voltage source. V is equal to I into R. I is 2 at an angle minus 90. R is 4. So multiply when both are in polar form. 4 into 2, 8. Angle is same. In series with the same resistor. Let us replace this by voltage source. In series with the resistance. Okay. Since it is AC, let us write AC symbol, and arrow was right side, hence I should write this is positive, this is negative. What is the value? 8 at an angle minus 90 volts. Resistance is 4 ohms. That way you can do it also. Now let us obtain Thevenin's equivalent circuit across the terminals A and B. Step 1. To find V Thevenin. What is the procedure? V Thevenin is nothing but open circuit voltage. Hence, create the open circuit, that is remove the load, create the open circuit and find the open circuit voltage. Let us remove the load, create the open circuit, find this voltage V Thevenin, that is your V Thevenin. To find the voltage, you can go by either mesh analysis or nodal analysis. So, as usual, I will go for mesh analysis. Only one loop you have, take this loop current as I1. So, this is open, no current is flowing. Let us apply KVL. What is the I1 now? From the network, I1 is equal to single loop network with only one source. So, Ohm's law, I is equal to V by Z. V is voltage 5 at an angle 0. What is the total impedance? 2 plus J4. Okay, that is I1 is equal to 1.118 at an angle minus 63.43 ampere. That means now to keep the calculator in complex mode, enter this value as it is in your calculator, keeping the calculator in complex mode. Then you will get the value 1.118 at an angle minus 63.43. Once you get I1, my intention is to find V Thevenin here. So, what is V Thevenin? V Thevenin is equal to potential between these 2 points is V Thevenin. Let us take this potential as VA, let us take this potential as VB, and potential difference between these two. If I take this is positive, this is negative, VA minus VB gives V Thevenin. That is VA minus VB is your V Thevenin. Now, to find the voltages, as I said earlier, in any network, we should have one reference point. Voltages are always measured between 2 points. If I want to measure voltage at this point, I should have another point. If I want to measure the voltage at this point, I should have another point. So, always potential difference means it is between 2 points. Hence, to measure the voltage at this point or to measure the voltage at this point, I should take one reference point. Reference point in most of the networks we take in the bottom line. You can take anywhere. You can take this itself as reference point. You can take this itself as reference point. So, but normally we take in the bottom line. Let us keep this as reference point. Then I have to measure the voltage at this point and voltage at this point. So, what is the voltage at this point? So, you have to move from the ground, that is reference, to this point. Either you can go by this way or you can go by this way. So, in that way, you should write the polarity of voltage drops or voltages. Suppose if I prefer to go by this way, you should write the polarity here, because polarity is not given. Suppose if you go by this way, you should write polarity here. So, polarity here depends upon direction of current. So, let us go by this way to reach this point. So, what is the polarity here? Current is flowing like this. This becomes positive, this becomes negative, because current is flowing downward, and voltage drop is nothing but it is from positive to negative is voltage drop. So, once you write the polarity of voltage drop, always to reach the point you should go from reference only. Okay. Now, then what is VA? Measuring voltage from reference. What is VA? VA is equal to, you go by this way, minus to plus is plus, what is the voltage drop here? J4 into I1, J4 into I1. So, J4 into I1 you substitute here, that is 1.118 at an angle minus 63.43. Okay. So, again keep the calculator in complex mode, find the value of VA. You get VA is here is equal to 4.478 at an angle 26.56. We check the answer keeping the calculator in complex mode. Next, what I want? I want VB. To measure VB, I had to go by this way only. I cannot go by this way. I have to go by this way. If you go by this way, here no current is flowing, no voltage drop, no current is flowing, no voltage drop, but you have this voltage source. Open circuit voltage will be there. So what is the voltage now? If you go by this way, plus 2 minus voltage is 8 at an angle minus 90. So you have to go like this only. Therefore, VB is equal to what? Plus 2 minus is minus. What is the voltage? 8 at an angle minus 90. So this is your voltage VA and VB. Therefore, substitute here V-Thevenin. And what is V-Thevenin here? So VA is equal to this, VB is equal to this. Substitute here and get the value of V-Thevenin. Then you will get the value 7.21 at an angle minus 56.37. Substitute VA here, substitute VB here. Again keep the calculator in complex mode. Enter that value VA VB. You will get the answer for V-Thevenin is equal to 7.21 at an angle minus 56.37 is your V-Thevenin. Step 2, what I should find? I should find Z-Thevenin. It is not a DC network, it is AC network. Hence, I should find impedance. Where I should find the impedance? Across the load terminals. Always under open circuit condition only, I should find the impedance. Okay. What is the procedure? You have to make all the sources in the network 0. You have to make all the sources in the network 0 and then you have to find the impedance value. Okay. Now let us find the second parameter Z-Thevenin. Step 2, to find Z-Thevenin. Okay. So what is the procedure to find Z-Thevenin? You have to make all the independent sources in the network 0. You have two voltage sources. Voltage sources are made 0 by creating short circuit. So create the short circuit and looking into the open circuited terminals, find the total impedance of the network. That is your Z-Thevenin. Let us create the short circuit. Okay. Let us create the short circuit here. Short circuit. Okay. Now looking into the open circuited terminals here, we have to find the total impedance of the network. That is your Z-Thevenin. Now this resistance and this inductance comes in parallel. These two are in parallel. Now I can rewrite this circuit like this. This is A, this is B, this is your Z-Thevenin. So these two are in parallel, that is 2 comes in parallel with J4, then these two are in series, that can be written as 4 minus J4. Okay. Therefore, what is Z-Thevenin? Z-Thevenin is equal to, so 2 parallel with J4, again plus 4 minus J4. Okay. This is your Z-Thevenin. Now this is what? 2 into J4 divided by 2 plus J4. Simplify, plus 4 minus J4. If you find this value, keeping the calculator in complex mode, you will get Z-Thevenin is equal to 5.6 minus J 3.2. So after simplification, the final answer of Z-Thevenin gives 5.6 minus J 3.2 ohms. This is your Z-Thevenin. Then step 3. Write a Thevenin's equivalent circuit. Thevenin's equivalent circuit. Write Thevenin's equivalent circuit and connect the load across it. What is the Thevenin's equivalent circuit? A voltage source V Thevenin in series with an impedance Z Thevenin. This is your Thevenin's equivalent circuit. Okay. So this is your V Thevenin value. So I'll rewrite this. Okay, this is your circuit diagram. So what is V Thevenin? You got the value. Z Thevenin, you got the value. Then what I should do? I have to connect the load across it. This is your load RL. This is 7.21 at an angle minus 56.37. Okay. So this is your Thevenin's equivalent circuit, and these are your load terminals A and B. Now you have to observe this circuit. What type of source it is? AC source. It is AC source. What type of source impedance? It is complex, because you are getting 5.6 minus J3.2, that is equal to 5.6 minus J3.2. And what is the load? Purely resistive load, and it is variable load. So what is the condition for maximum power transfer? It is second case. Source is AC, load is purely resistive, and it is variable load. The condition for Pmax is the load resistance should be equal to magnitude of source impedance. So when source is AC, load is purely resistive. Load is purely resistive. The condition for Pmax is RL should be equal to magnitude of Zs. RL should be equal to magnitude of Zs. This is the condition for maximum power transfer. What is Zs here? Zs is nothing but Z Thevenin. Here Zs should be equal to Z Thevenin. What is Z Thevenin here? Z Thevenin is equal to 5.6 minus J3.2. Okay. Now this should be equal to magnitude. What is the magnitude now? Magnitude of Zs is equal to the root of 5.6 square plus 3.2 square. If you enter in calculator, you will get this value 6.44 ohms. Therefore, RL should be equal to magnitude of Zs is equal to around 6.44 ohms. This is the value of load resistance for maximum power transfer. So after getting this value, that is 6.44, I should find the power also. To find the power, take the current here, load current. So what is the load current? IL is equal to V Thevenin divided by Z Thevenin plus RL. Z Thevenin plus RL. Now find its value. Now substituting the value of V Thevenin, Z Thevenin and RL here, and keeping this, entering this value in calculator, keeping the calculator in complex mode, we get the value of IL is equal to 0.57 at an angle minus 41.4 ampere. After finding the value of current, you can find the power. So Pmax is equal to I squared into RL. So to take the magnitude here to find the power. What is the magnitude here? 0.57 whole square, and RL is what? 6.44. So calculate the value of power, you get 2.13 watts. This is your Pmax. Okay. I hope all of you have followed this problem. Let us work out some more problems on maximum power transfer theorem in the next sessions. Thank you.